This conference will now be recorded.
Wonderful. So, in today's session, we're going to look at one of the interesting topic in terms of the advancement in the AI field as such. So, this is the agenda that I have put together, and as I was putting together the presentation, the lot of content, the context I have to provide, and the total slide has gone to 60 slides. I will try to cover as much as possible in the today's session. If it not, probably I would like to take the whole premise into two different sessions so that in today's session you understand the basics, logic behind what we are trying to achieve, and in the future sessions we can go over the code and a deeper understanding of the neuro-symbolic AI as such. Okay, so in today's agenda, we will look at what is the problem the current AI and the ML approaches that we are doing uses, and we provide an introduction of what is a reasoning as such, and then we will introduce what is an introduction to a symbolic AI and a combination of the neural network and the symbolic AI and the new field of research have brought in something called a neuro-symbolic AI. Why this is required and what is the current progress? IBM has released something called the logic neural network, which is the state of the art neural network architecture in terms of combining the symbolic AI with the neural network architecture. So that is the whole premise of it. But before we go to LNN, we should have an understanding of what is the current problem, why we need this approach of working with something, a new type of a logical neural network. So that is what the context that I will try to provide so that all of us are in together to understand this whole premise as such. Okay, so before I start, let me just take a step back that what is the current approach of any machine learning problem solutions. You typically start with your data part, and once your data part is ready, you will go for an experimentation part. Once the experimentation is done, you iterate on that experimentation to find the proper model. Once the proper model is received, you basically go to a production and deployment. And typically, if you look at it is not a one-time activity as we typically do in a typical software development. Majority of the machine learning developments were a cyclic process where you gather some data, you prepare the data, and based on the data that you received, you train the model, you test the model, and you deploy the model. And it does not stop there, where you again go for fine tuning your model to achieve an optimal outcome from the machine learning life cycle as such. This is the typical process that we follow on any machine learning project, right? So let's take a simple example. In case you wanted to build a system where for a bank, you wanted to create a loan approval rejection process. To do that, you basically go to the bank and identify some of the data or some of the processes that are being followed at the bank, and you try to collect the data specific to the bank. And once you collect the data, you apply various algorithms to specific to the data that you receive from the bank, you come out with a model. And once you receive the model for that bank, you deploy that particular model, and the bank will start utilize that model for your loan approval or rejection process. Okay, so there are various question comes into the whole ecosystem. So now the mod you have spent so much of time, could be 3 months, 6 months, understanding the data, cleaning out, and coming out with the model. You have done a phenomenal work, and the outcome is only utilized by only that bank or the insurance company that you are working with. So what is the purpose? Can't we actually use the work that you have done, for so many months that you have put? Can you use that knowledge? can't you use that outcome of that particular one for any other you know problems which are similar to that? But the current machine learning approach is each and every problem is considered as a new one, and each and every problem is addressed in a very unique way. So that is a very basic problem with the current approach. Let's look at some of the shortcoming. The low reusability. We cannot reuse this model. Let's say you created this model, fantastic. Can I take the same model and put it into a different bank? It may not work, and the final outcome that you're going to get is going to be a complete pathetic outcome. And the second thing is the intelligence that you are looking at from your machine learning model is you want that model to be much more intelligent. But is it doing any intelligent operation as part of the actual uh, loan approval process? It does not. In the sense, it typically takes a typical if then else statements that you normally do. Instead of doing an if then else statement, it basically extrapolates that to a mathematical formula and use that formula to solve that particular problem. That's it. And be it a neural network, it is a combination of an algorithm which does that with a large amount of data. But if you ask some questions to that model that you have built, which is outside of the whole premise of the loan approval, the model typically fails because the model is not that intelligent enough. The model is not reusable. The model is not that much of intelligent enough. So the current stage of AI or the machine learning development that we are doing is predominantly called artificial narrow intelligence. In the sense, you don't focus on solving at a very large common problems that you are trying to solve. And the last problem is not much reasoning capability as available there as part of your model. You built it for credit card or your loan approval process. Can I use that for say credit card approval process? You may not be able to. Or can I ask some other question related to the customer to the same model? You may not be able to, because model is dedicated for that particular one. Specific to the last point I wanted to stretch upon, because that is one area where majority of our recent developments were not focusing on, and that represents that we are not in the right direction. So what is the right direction that AI development has to take to actually go to the next level? So that is the whole premise of our today's conversation. Okay, let me take a minute to understand and appreciate what is that not much of a reasoning capability that is there. Let's take a simple example. So let's say that there are two premises are available. One, let's say all humans eat vegetable, and there is a premise there, Suresh is a human. I'm just taking a hypothetical example. As a human being, you can very easily reason that all human beings are vegetable, eat vegetable. Suresh is a human, so you can conclude that as a human being, Suresh eats vegetable. Okay, it is such a very easy outcome that a human being can take. But if you look at, if you want an AI model to do this at the current juncture, it is a very complex activity. In turns, you may need to provide huge set of training data for the model, and you may have to train that particular model to tell that Suresh is a human, so Suresh can also eat vegetable. So this current approach of the ML uh, does not do much of a reasoning as such, but it tries to actually come out with an approach, best approach of finding what is best for the problem that you are trying to address. So now, how do we build a system which has similar to our human beings? I mean, the human being think. How can we make the system think like a human being? So that is a basic question. Okay. So now the AI goal. as such, if you look at, we wanted to take the artificial narrow intelligence currently that we are there to a level of something called artificial general intelligence. The artificial general intelligence meaning it should be the model that you are creating should be an universal model. It should be able to understand and appreciate a lot of different conversations which is happening. The model that you build should be reusable across multiple areas. The model that you build should be able to reason what is going on in the actual conversations. That is artificial general intelligence. But we don't want to stop there. The goal is basically to go to the next level of artificial super intelligence, and that is a long way to go. So currently, if you look at, we are currently in the artificial narrow intelligence stage, and there are some breakthroughs that we see, like that we see in terms of neuro-symbolic. This is like the this is like of this, that is the current level currently we are in, where um, big throw and in a couple of years we could be reaching.
Hi, Prasanna. Prasanna, is it?
Yeah, you're able to hear me okay?
No, Prasanna. It's I many times I got like disturbance, like it's going completely low and coming after that sometime. Is it
Okay,
for anyone else or only for me? I'm not sure.
got it. I think there is some internet problem from my side.
Hmm.
You're able to see my screen?
Yes, Prasanna. We are able to.
Okay, wonderful. Thanks. Okay, so what are all the different research initiatives which are going on? So whatever that I'm going to present now is a very limited number. There are so many other research are going on. How do we achieve or reach the artificial general intelligence? So the first approach is something called evolutionary computing approach, which uses genetic algorithm as an approach for reaching there. And the next is using symbolic AI. The recent advancement is in terms of utilizing neuro-symbolic AI. And there is a graph-based AI, deep graph neural network. There is deep reinforcement learning based approach like deep Q learnings, and you have approach in terms of Bayesian networks like Bayesian neural networks, where all some of the examples. This is not the finite list where there are so many other approaches were also going on parallelly in terms of quantum machine learnings and so on and so forth, where all these approaches were trying to move away from artificial narrow intelligence to artificial general intelligence. So that is the goal of all these research initiatives which are going on in parallel. So now in our today's session, we're going to look at how a symbolic AI and the neuro-symbolic AI is going to be the approach for achieving the artificial general intelligence. So before I want to start this whole premise of symbolic AI and neuro-symbolic AI, I wanted to just start with an interactive session with all of you, just to think about it. So I'm sure all of us have seen this video where this robot is developed by Boston Dynamics. The purpose of this robot is basically to automate package delivery or package management and arrangement. So that is what it is currently doing, and it is an AI enabled robot. Okay, so now if let's say Boston Dynamic is coming to us and saying that you guys have to design this robot. What is that from an AI perspective? How shall we approach uh, to design this particular AI system? We are all software guys, I understand. We don't need to go to the robotics part. We understand from a software perspective what are all the different things that is essential for us to actually build this robot to operate, to arrange these boxes. I wanted to understand from you guys, what do you think? It is just nothing wrong, nothing right. It is only to enable us to do an interactive understanding of how can we design this robot, an intelligent robot. Anybody?
Maybe finding the space, what is the current space, the
Okay,
first thing,
okay,
and what are the different paths where it needs to really travel rather than we are telling the road, it should understand which is the road, which is the item where it needs to place. Second
very
thing,
nice. Okay,
maybe how to handle at least a item to place somewhere. Maybe it might be most into robotic rather than software, definitely.
wonderful, wonderful. Yes. So,
That I
can
think so.
we, yeah, yeah, go on. Yeah.
That's all, Prasanna. Moreover, that is the major, I think so.
So, effectively, what you are saying is, so there are certain set of activities that are being done that you wanted to instruct to the robot. So there is a certain knowledge that you wanted to incorporate for this robot so that this knowledge can help the robot to perform well. Is that a fair understanding?
Yes, correct, Prasanna. It should understand what is the item, which is the road. It should understand what is basic first. Yes, you are right.
Exactly. You are absolutely correct. So, so the so one thing is there is a set of knowledge which talks about what is the activity that this robot has to perform. What is the activity in terms of it needs to take this 10 lb of box and put into that particular tray location. So the first thing is what is this box it has to take, the knowledge about where it is available, how it has to lift, how it has to place. All these are some kind of a knowledge information that we need to give it to the robot. The second thing is what activity, what actions that particular robot has to perform. So actions in terms of it has to first grab the box, it has to lift the box, and it has to place the box. So these are some of the actions that it is performing. So this is what we a typical robot, or I would say an AI agent, is going to actually perform. So to summarize the understanding, the expectation of an AI system or an AI agent is an intelligent agent needs a knowledge about the real world for taking decisions and reasoning to act efficiently. Okay, so there are two important pieces here. So as a robot, if it needs to actually perform some activity, there should be some knowledge about what is that activity that it has to perform, and there should be a real world interaction happening. In the real world interaction, there could be multiple things happens. Probably the box could be open or the box could have fallen down. If it falls down when the robot is trying to take, what action it has to take. So the robot should basically understand what happens in the real world scenario. Based on that understanding, it has to take a different actions. It may not be the same actions all the time. It may need to walk to a certain location, and if it needs to walk to a certain location, it needs to perform an action based on some of the thing it is seeing in the real world, and based on that real world reasoning, it has to take a decision in terms, okay, the box is there in 10 meters, I need to walk towards there to the 10 meters and pick up that particular box, and put it into a shelf which is in 20 meters. So this actions, reasoning, and the knowledge all works together in a real world scenario. So that is what the actual AI agent is expected to do. So to summarize this particular activity into a pictorial form, we can think of the whole robot interaction as an environment. So the first thing, when a robot is switched on, it will first look at the environment where it is currently standing. It could be using various different things. It could be using your vision, it could be using various sensing sensors. And all these sensors are going to help get this input from the environment. There is an inference engine which actually understand what is there, what is happening in the environment. And the inference engine also goes to the knowledge base and identify what is that it has to do. So the activity assigned for the robot is in terms of it has to go and pick up the actual box. So then based on that knowledge base, it actually performs an output, performs an output. To even go to the next level, there is a decision making happens for on each and every second at the robot. There is a sensing that happens, and the knowledge base is giving the intelligence required for the decision making. And based on the knowledge that it receives from the knowledge base and the sensing input, it takes a decision in terms of what action it has to perform. And so there are two important pieces to the AI knowledge cycle. This is called AI knowledge cycle. So there is a perception layer. The perception layer basically is from the sensing infrastructure for the robot, where the sensing infrastructure provides that information. Um, um, Sensing infrastructure provides the current state, and the knowledge representation basically provides the information about what the robot has to do. And there is a reasoning layer. The reasoning layer utilizes the current perception and the knowledge and takes the next steps in terms of an execution. To give you a robotic perspective, the robot is standing, it uses the perception to see where the boxes are, and it goes to the knowledge representation to see what is the activity it has to do. Basically, it sees that it has to take the box and put it into the shelf. And assuming that the box is in 10 meters away, so the reasoning understands that it is 10 meters away. The reasoning basically instructs the robot to walk towards that particular box. There is an execution happening. There is a planning, there is an execution that happens by the reasoning. Once it reaches the box, it basically goes and picks a box and put that into the shelf. So this is the representation that is being mentioned, where two important pieces are very, very important in terms of building any AI system. So one is in terms of knowledge representation. Second is in terms of reasoning, how the actual environment is perceived by the whole robot as such. So this expanding this approach is what is going to help us reach to the AGI. Okay. So in today's session, we're going to focus on the two important pieces on the AI knowledge cycle. One is knowledge representation, second is the reasoning. So we are going to dig deeper into what are all the different approaches of knowledge representation which are there. What are all the reasoning approaches are available, what is best is being used in the current scenario for making a robot to interact with the world in the real world environment. So that is what our today's focus is. Okay, so let me start with the knowledge perspective. So the ideal goal of an AI agent is understanding the knowledge and representing the knowledge in a proper way, and it has to reason from the knowledge. It has to understand what is going on in the knowledge as such, and that will enable us to reach the final goal of goal of becoming an ideal AI agent, right? So we will let us start with understanding the knowledge um, part. So the first, before we understand the knowledge, we need to define what is knowledge. What are all the different knowledge options are available? How do we actually effectively represent a knowledge there? When you worked on any machine learning project, basically you might have used data frames, your pandas, and so on and so forth. So this is one form of representation of the knowledge. It is just a tabular form of representation of the knowledge. So if you look at the knowledge representation, there are multiple ways you can represent the knowledge. A simple relational knowledge, inheritable knowledge, inferential knowledge, and procedural knowledge. So the reason why we need to understand this is we have all these are going to become a base for our neurosymbolic AI. So this you need to understand the basics so that that can help you understand the neurosymbolic AI better. So in a these are four knowledge representations. So in the case of a simple relational knowledge, we all have been using this. A typical database table is a simple relational knowledge representation. You see a player information that is being represented here. And the important second approach is inheritable knowledge. When you see the screen where the informations are presented in a inheritable way, where there is an is-a relationship is being represented here. Okay, so for example, we all know from a programming background, we might have worked on some object-oriented programming where we all were aware of an inheritance workflow where Peter is an instance of a cricket. He is basically a person who plays cricket, and there is a football, and Ankit is basically an instance of a football match where here the relationship is a relationship that we are trying to build where Peter is a player who plays cricket and Ankit is a player who plays football, but both are basically adult male. So that is what an inheritable knowledge is being represented here, where in the case of tabular form it is basically two set of informations are being represented here. The is-a relationship provides three set of details. So there is a player in cricket, there is also a player in football, and there is the adult male is a player. So all these are represented with three set of informations there. Okay, this is inheritable knowledge. And the next is inferential knowledge. Inferential knowledge in terms of, let's take this example, it is much easier. Let's take that Marcus is a man, all men are mortal. Then the representation can be represented as Marcus is a man for all the men who are considered as X, they can be considered to be mortal. So this is one way of representing. It is an inferential knowledge representation. So we are inferring from the actual facts which are being shared to us. That is inferential knowledge. The fourth is basically procedural knowledge, where sorry for the typo there. It's a procedural knowledge. Procedural knowledge in terms of um, we all are aware of your programming languages where you do a if then else statement is an example of a procedural knowledge as such, where the details are represented in a code program format or a code format, and these programs were executed uh, by some programming language. Okay, so these are four different way of different type of knowledges which are available. So now we have looked at understanding knowledge. The next is how do we represent this knowledge. It is very important before we get into there. because as a machine learning engineer, you might have already known that you might have taken some tabular data, did some ED on the data and started utilizing your data for your machine learning model creation. But is it the right approach? That is the question that we are doing. So to do that, we have seen understanding of the knowledge. There are four different approaches whereby the knowledge can be derived. And the next is, how do we represent the knowledge? So there are four different approaches. There is a logical representation, there is semantic network based representation, there is production rules based representation, and frames based representations. Okay, these are knowledge representations that we are talking about. So what is the knowledge? Like you have seen, robot has to actually perform that activity, and robot has to take the box from one location to another location to put it into the shelf. So to instruct the robot, you need to give a knowledge to it. So that is what we are looking at. How you can actually give the knowledge, and what are all the different approaches with which you can provide the knowledge to the robot, so that you can actually make that robot as an intelligent agent. So now we looked at what all the different knowledge are available, and now let us look at how can we effectively represent this knowledge there. Logical representation, semantic networks, production rules, and frames representation. So logical representation, this is very very important, because this is logical representation makes as the basic premises for our symbolic AI and the neuro-symbolic AI. So whatever that we are looking at is based on the logical representation of the actual data. So the representation can be as syntax and semantics were two important part of a logical representation. There are two types of representations are there. One is proportional logics, second is predicate logic. This is the two important thing we're going to see fully. I will have a separate set of slides. I will talk about it. First, let me just give you a context about what are all the different knowledge representation. I will go to the proportional logic and predicate logic. So logical representation, the first is logical representation. I will explain to you in detail about proportional logic and predicate logic. Let's just hold on for a minute. Semantic network representation, this diagram explains about a semantic network representation of the knowledge, where all the details are connected like a graphical representation, where each and every node are connected to another node with some kind of a relationship. It is a semantic network relationship. It's a graphical representation of your knowledge. You can consider Google currently uses this, large graph based knowledge base for their search algorithm. Similarly, many of the large organization utilizes Amazon's products are categorized using a semantic, like graph based approach of managing their product information. So these are some of the representation in terms of large data entities by large companies are following this approach of managing their relationship as such. Okay. So the third is frames representation. I'm sure most of us might have seen the details in Wikipedia. In the Wikipedia, if you look at, you might have seen some details about any specific person or details that you are searching for. These details are not hand coded majoritarily, and these details are derived from some of the data that are available uh, in the public domain as such. So the representation is called frames based representation, where from the existing knowledge these frames are being kept updated, so that these informations are being extracted from multiple locations and gets updated. It also allows you to edit and modify this information, but just this is a frames based representation. So the frames based representation consists of two things. One is slots and filters, and it talks about, let's say there is a book that you're talking about, and the book consists of, these are different slots that covers, and these are some of the details about that particular book. effectively. Similarly, if you talk about a person, these are different slots, and these are some of the details about the particular slot. So that is what is covered part of this. This is a frames representation. The next is production rules representation. Production rules are like predefined set of rules that you define. For example, I don't want to have a dynamic activity to be done for this particular robot. So instead of giving a dynamic activity, I wish to have this as a static set of production rules. So if that robot has to take that particular box and put it there, I can define these rules as if then else statements, so that the actions are directly provided to that particular production rules. If at a bus stop and bus arrives, then an action is go into the bus. Like you are instructing that particular robot to actually perform an activity. So that is production rule. So there are four different types of knowledge representation we looked at. We looked at first what are all the four different type of knowledge itself, and then how we can effectively represent this knowledge. There are four different types: logical, semantic, production rules, and frame sets, frames representation. Now, as I said, I will come back to the logical representation because our focus is on how we effectively our how we are effectively providing the logical representation. So the first one I wanted to start with is a proportional logic. The proportional logic is the simplest form of logical statements, where the statement has to adhere to something, either it has to be a true or false statement. So, which is a very prominent form of representing the knowledge. If you don't understand, don't worry about it. I have a lot of examples to explain to you. Um, Whenever some statement that you are talking as a human being, so it can take two states. One is either it is a false proposition or true proposition. We can represent all the false, true or false statements as a proportional logic representation. We all know that sun rises in the east. So if it is sun rises in the west, it is a false proposition. So 3 plus 3 is 6. We know it is 7. That is a false proposition. So the basic thumb rule is they all has to follow a Boolean logic. Either it has to be 0 or 1. The proportional logic can have multiple symbolic variables like A, B, C, something like that. And it can have both either a true or false. It cannot have both at the same time. And there are logic connectors which are going to help us connect with this. These are called logic operators. And there are certain statements in a real world scenario which cannot be a proportional logic. For example, so I can ask, how are you, Mali? So this is a statement or a question. This cannot be a proportional logic. This is one of the problem with the proportional logic, and let us see in a minute how we are actually solving this problem. Okay, so these are some of the conditions. So there are two type of proportional logic. One is atomic proportions, and the second is compound proposition. Atomic propositions, for example, it is a fact, and either it takes true or false. A single statement or single item, atomic items are considered for this particular one. Sun is cold. It does not have a complex statement. It is a simple statement. It is an atomic proposition. So that is false. So that can be considered as an atomic proposition. And if you go for a compound propositions, it is like two different set of items are being considered. It is raining today and street is wet. There are two different kind of, two or more, you can consider two or more kind of atomic propositions combined together will form a compound propositions. Okay, so this is atomic and compound propositions. Now, what is the logic connectors that we are talking about? The logic connectors help connect multiple propositions that we are talking about. For a programmer, this is a very easy one. where we might be doing it on a day in day out basis, but there are some specific differences. Let us see. We have seen and or implies represents A implies B. If and only if A, if and only if B, or not, all these are negation operation. These are some of the logical connectors that we use in the propositions as such. So using this proposition logic, we can come out with something called a truth table. What is this truth table? Is when you apply this particular proposition based on the value of this particular each statements, you come out with an outcome. For example, if negation as a proposition, if you take, if a statement is true, a negation of that statement is false, and vice versa. And if there is a conjunction statement, conjunction is and statement. So the conjunction statement, how it is going to work there. So if one is false, it is considered to be false. There is an or statement which is a disjunction function, where if one is true and the output is true, and both are false, then only that output is considered to be false. Okay, so these are the propositional logic will derive the details from the derive the details outcome as part of a truth table to understand how the logic actually works. So now, propositional logic, one of the basic problem that we looked at, all the statement has to be true or false. It does not include the details in terms of what is going to happen if I want to include some real world scenario. I told you, like, how are you, Mali, is a real world scenario, but effectively proportional logic does not support it. So that is where a new type of logic representation called first order logic came into existence. So the first order logic was built basically to solve, it is an evolution of this proportional logic. Just to give you guys a background, why are we talking about this is basically this is going to give us the premise for our logic neural networks and so on and so forth. Okay, so the first order logic as such, some example, you can say some humans are intelligent, which is not a true or false statement. Is a very generic statement which cannot be connected to a proportionate logic. So that is what it is trying to solve. The first order logic is trying to solve. So the first order logic is also called a predicate logic. We talked about proportional logic and predicate logic. So this is the two things that is going to rule our neuro-symbolic AI. Okay, so the first order logic is a very important part of neuro-symbolic AI. So that is where we are looking at this, where first order logic is sufficiently expressive to represent any natural language statements in a very conscious way. Let's see how it happens. Along with the proportional logic, on the first order logic, you can represent objects, you can represent relationship, you can represent functions, and it also comes with syntax and semantics as part of your first order logic. Okay, so what I meant by that, the basic elements of a first order logic is it can contain constants, it can contain variables, it can contain predicates, and it can contain functions, connectives like what we mean and or not, negation and all. Equality in terms of this is equal to the second item. A quantifiers in terms of for all there exist, all these quantifiers can be represented there. Do not worry if you think it is very complex, it is very simple. Okay, let's take a simple example of Ravi and Ajay are brothers. We can represent them by using a brothers as a predicate, and Ravi and Ajay are part of that particular predicate. Chinky is a cat. You can represent them in the first order logic like cat is a predicate, and here Chinky is a cat. So that is what, this is how you basically represent the details there. And also you can use more complex item as well. For example, x is an integer. It contains a subject which is nothing but an x, and predicate which is an integer. All men drink coffee. So drink is the predicate, and all men are basically the actual subject, and that can be represented there. For all men, a drink is a predicate. For all the men, drink coffee. That is how you represent in the first order logic. Okay. So this is a way of representing first order logic details. Okay. So till now, what we have done is we understood what are all the different types of knowledges are available. We looked at what are all the different representation of the knowledges are available. Representation in terms of, we looked at first order logic, we looked at proportional logic, we also looked at semantic, frame based, we looked at an approach of production rules based knowledge. So these are some of the representation of the knowledge. You can choose any of these representation of the knowledge, and you can expand up across for instructing to the robot that we have taken. You can choose a type of knowledge, you can choose a representation of the knowledge, and then go and instruct the robot that what it has to do. Now when you give this knowledge, the robot should know how to learn or reason this particular knowledge, right? It has to understand how that knowledge can be translated into some actions. It has to understand what is happening in the environment based on the inferencing that it is doing. So that is what we are going to look at now. So the reasoning as such, the robot has a knowledge base now, assuming that in one of the first order logic you have given all the different instructions for the robot, all the different instruction in terms of how the robot has to actually act in the whole situation. So that you have already provided to the robot. Now the robot has to reason from the knowledge, robot has to understand from the knowledge. Let us look at what all the different reasoning approaches are there. Okay, so these are 6 different reasoning approach which are connected to the different knowledge representation that we talked about. There are some more approaches are there, I will talk about it at the end. Okay, so these are for the defined or detailed knowledge that you already have. You have created a knowledge base with the detailed set of instruction for the robot. Now the robot has to understand how to reason from it. So these are 6 different approaches by which the reasoning can happen. So what is the reasoning? So reasoning, there is a simple example, let me give you here. So the reasoning is very simple. So premise 1, let's say all humans eat vegetable. This we have seen. Now a premise 2 is Suresh is a human. From this AI, we want AI to reason that Suresh eats vegetable. Suresh eats vegetable. So that is nothing but a reasoning. So you, from a robotic perspective, the robot takes the box, but the box fell down. Now, if the box fell down, by looking at the environment, the robot should understand that the box has fell down. It has to do an action of taking the box again. So this is the reasoning that we are talking about from a robotic perspective. Okay, so these are different reasoning by which we can actually achieve that. Let us quickly look at what is this reasoning and how does it different from each and every one. So the first is a deductive reasoning. So deductive reasoning is at deducing new information from logically related known information. For example, the example that we have taken in the previous example, where all humans eat veggie and Suresh is a human, you are deducting as that Suresh eats veggie based on the information, the premise that is being provided to you. If more informations are provided, you will come out, you will deduct what is the conclusion out of it. So that is deductive reasoning. Next is inductive reasoning. Inductive reasoning, where you have only a limited set of facts. Limited set of facts are available with you, and you need to come out with a generalized approach. Okay, let's take only a limited set of fact. All of the pigeons we see in the zoo are white. Okay, so all the pigeons that we have seen in the zoos are white. So the conclusion, the reasoning that you have to come out is, we can expect that all the pigeons are white. Okay, so it is not explicit, but in the zoo you have seen all the pigeons are white, so you come to a conclusion, sir, pigeons are white, right? So this is an inductive reasoning. Next is abductive reasoning. So it is a uh, form of reasoning where it starts with a single or multiple observation, and it tries to come out with the most likely explanation or a conclusion from the observation. Let's give an example. So let's say an implication is, cricket ground is wet if it is raining. This is a very simple statement. Let's take that this is a knowledge which is already given to you. Let's take an axiom that is being given to you, like cricket ground is wet. So now, because you already have a pre-observation, pre-details knowledge available that cricket ground is wet if it is raining, you can come to a conclusion that because cricket ground is wet, it is raining, right? So this is abductive reasoning. So the next is common sense reasoning. So we all know, we all have some common sense reasoning in terms of many facts we cannot change. Um, for example, a one person can be at a place at any point in time. If I put a hand on a fire, then it will burn. So these are common sense reasoning. So these reasonings are facts that cannot be changed. The next is monotonic reasoning. Monotonic reasoning, for example, once a conclusion that you are taking as an AI agent, even if you add some new new inferencing, you will not, the whole reasoning will not change as such. For example, so Earth revolves around the sun, which is, we all know that, and this is a conclusion assuming that the conclusion is derived. But now let's say you are adding some more facts to it. The moon revolves around the earth. It is not going to change this conclusion. Earth is not round, which is not going to change this particular conclusion you have taken, which is monotonic reasoning. Okay, you have come to a conclusion. This conclusion will not change even if you add as many new facts as possible. Okay, that is monotonic reasoning. And the opposite of that is non-monotonic reasoning. Well, let's look at an example where we have three facts here. Okay, based on these three facts, you come to a conclusion. But as new facts are getting added to the conclusion, you see that the whole premise is going for a toss. Let's see an example. Non-monotonic reasoning, where birds can fly, is first knowledge. A penguin cannot fly, it is also a knowledge. And the third is, pity is a bird. Then these are three knowledge that you have received. Based on this, you can come to a conclusion that knowledge agent, a agent can come to a conclusion that, can a, because it is a bird, then pity can fly. Pity can fly. But now you add one more knowledge base item into this. one more statement that Pity is a penguin. So now, as soon as you add Pity, then you can decide that Pity cannot fly. Okay. So this is an example of how some non-monotonic reasoning, where you add some details on the existing knowledge base. When you add some details, then the reasoning will change based on the new knowledge that is received. So we looked at deductive reasoning, inductive reasoning, abductive reasoning, common sense reasoning, and monotonic and non-monotonic reasoning. So these are multiple reasoning approach by which your AI agent can perform very well, understand very well what is going on. Okay. So all the reasoning approach that we looked at were based on facts. Bird can fly. It can either be true or false. That's it. Okay. But there are cases where you cannot possibly expect the same outcome for a reasoning. In this case, mathematics is an example where you may have to derive something out of that, or probabilistic reasoning is an example of where, when you have a situation where the outcome is not known to you as a true or false, the outcome is in between true or false, it is a probability of an event. Okay. Example, a probability of, it is going to rain today. There is a 50% chance that it is going to rain today. There is a 60% chance that it is going to rain today. Now, does it mean that it is going to rain? It is not, because it is a probability that you are attaching to this statement. It cannot be taken as a true or false statement, where it has to be taken like a probabilistic reasoning in AI, and based on which you may have to take a different kind of a decision there. I hope we have covered well enough information on what we're talking about in terms of AI agents goal. So we looked at in the presentation initially on what is the problem the current AI and the ML process faces, and to solve that problem, what are all the different AGI research approaches are happening. And in the AGI different approaches, the first problem that we are trying to solve here is using a neuro-symbolic AI. So to understand neuro-symbolic AI, first we need to understand how the representation of the knowledge actually happens. What is knowledge? We need to define. So that is what we did. We started with defining what is a knowledge. And once we defined the knowledge, then we looked at what are all the different representation of the knowledge, how we can actually represent this knowledge for a robot to actually effectively work. Once we represent the knowledge, we looked at how we can actually reason the details from the knowledge. Reasoning in the sense, we looked at multiple different approaches the reasoning can happen for the knowledge as such. Now, once we reason, it can take action. So that is where our ideal AI agent will come in. Okay. So this is the goal of an ideal AI agent that we wanted to achieve. Before I move on, I would like to take a pause and try to understand, is this clear? Do you have any questions on this? And I wanted to understand from the team. You can just put it on the chat also. Wonderful. Yeah. Right. So now, till now, what we looked at is in terms of how do we represent the knowledge, how do we reason from it. Okay. Now let me introduce you to the next set of items. Let me introduce you to a symbolic AI. So basically, what is symbolic AI is, when we are talking about computers, the computers see things in zeros and ones. Even in the machine learning, when you wanted to perform some activity on a natural language processing, it does not do anything in terms of actual language, where you may have to create a machine understandable embedding format, and only that embedding you will give it to the machines. Basically, machines see only zeros and ones, right? But the human assets see things in the real world as real objects. When you are in an office space, you see a chair, you see a man, a desk, and details. These are, you can represent them as symbols. Okay, these are can be represented as symbol. So till now what we looked at is as these all as a knowledge base, and how do we represent the knowledge base is what we looked at. And the knowledge base can have a symbols and their relationship. So from where this symbols and relationship comes in, that is based on the first order logic that we looked at. So symbolic AI utilizes the proportional logic and the predicate logic, the first order logic that we looked at, for representing the symbols and the relationship. Okay, so let's look at an example. uh, so here, a person eats a bread. Here, the person and bread are represented as symbols, and eat is represented as a relationship. And this is a relationship representation. Similarly, you have logical connections. A person eats a bread, you can represent them using an and or logical connector. There is an implication. If a person is hungry, then he eats bread. This is an implication that you are representing here. So this is how typically a symbolic AI theoretical representation actually happens. What we are talking about is a real world human representation. That is what is happening. So where is it being used? So we all were aware that Apple uses Siri. Siri used on the initial days. Now they have moved on to larger deep learning based NLP models. But Siri on the initial days, they have used the symbolic AI for the knowledge, understanding, and the representation as such. So the advancement on this symbolic AI combining with the neural architecture is called neuro-symbolic AI. So I hope you understand the premise of how we have evolved from understanding the knowledge representation, understanding the reasoning, to a symbolic AI based representation. Okay. So now let's go to the next level of information uh, in terms of what is the current deep learning approach that are being happening, and how multiple progress were combined together to build the neuro-symbolic AI as such. Okay, so as I told you, I will probably give you the context, and then we will go to the coding and the detailed deep understanding of the symbolic AI in the next session with some code examples as well. Okay, so now if you take the current deep neural network, the basic neural architecture with the probability is what derived or brought in the deep learning that as we know it. Now there is another approach that is happening in parallel on the AI world, where the logic representation along with probability is what the symbolic AI basically brings in. Now, what there is another way of looking at thing, a logic representation with the neural architecture, which is also going on. The research is going on, which is a neuro logic approach of representing the AI. And the neuro-symbolic AI basically combines all three approaches, where you have a logic based representation of the knowledge, you have a probability for your managing the facts which are not either 0 or 1, and your neural approach for much faster representation of the details. That is the premise, a combination of a logic representation of the data and the neural architecture, the deep learning architecture with the probability, were all combined together to bring the neuro-symbolic AI, right? So I would like to stop here in terms of where I've given you the intro on what is this neuro-symbolic AI, and we have looked at the first order logic and the knowledge representation, the logic representation, knowledge representation. These two play a very important role in terms of how the neuro-symbolic AI actually works. So we will cover in detail about what are all the different components of the neuro-symbolic AI, and a specific type of architecture called logic neural network, which combines the logic representation that we looked at and the neural network architecture to bring in the advanced features, which is considered to be more advanced than the typical deep learning approach that we are currently having, because it can represent, it can do a reasoning at a much better way. So that is the premise of the neuro-symbolic AI as such. Okay, so any questions, team, till now? Okay,
Clear,
so
Prasanna. Thanks.
sure. So if there is no questions, I would like to pass here so that we can continue, because there are a lot of theoretical knowledge. I don't want to drag to more technical details. That will reduce the interest. So I will have another session where we will start from here where we left, and we will go deeper in terms of code level understanding of logical neural network and how things are working. Okay, so if there is no any questions, I'm happy to answer. If not, thank you very much for joining the session, team.
Thank you so much, Prasanna. Very clear. Waiting for the next.
Sure. Thank you very much.